So we're going to consider the relationship of volume with temperature and pressure. So we said before that we had our liquid, and when we heat it, so if we have a piston in here, as we heat it, the piston will move up and our gas will adopt the whole volume. If we plot this as a graph, so we're just going to plot volume against temperature, we have this straight line. And what we can say is that volume is equal to a constant times the temperature. So we can give this a constant. If we have our gas and we have our piston and we now apply pressure and we're going to compress this, you can see we compress it. And if you remember, we said that it eventually goes to liquid, but we can make the volume smaller. We can plot volume against pressure and we end up with this kind of exponential decay. And we can write this mathematically and we can say that our volume equals a constant times 1 over the pressure. Okay, so this starts to lead us into trying to understand how gases behave. And the behavior of gases is reasonably well understood. And there's a long history of lots of different scientists investigating it. And then back in 1662, I mean, hard to conceive that this work was being done that long ago, Robert Boyle did some work on gases, which basically led to what we now know as Boyles Law. And what he said was at constant temperature, the pressure times the volume is equal to a constant. And what this is a macroscopic law. So we've made no assumptions about the microscopic system, so what the system is. And we've not considered the concept of atoms or molecules at all. Okay, we're just literally taking an arbitrary gas and we're saying that the pressure times the volume is equal to a constant. In a bit later on, the volume of gases was studied by Gay-Lussac, and he led to given Waals Law, which is the scientist that inspired his work was Charles. And what he said was that constant pressure, the volume is equal to this V0 term, which is effectively the volume at 0 degrees C, times 1 plus alpha T, where T is the temperature and alpha is the coefficient of expansion. And alpha is typically found to be about 1 over 270. And the modern value is 1 over 273.15. And for the eagle-eyed amongst you, will know that that's the conversion rate to convert degree C into Kelvin, so the absolute temperature scale. So we can see here, we've already stated that a volume of gas, if we have constant pressure, it will increase linearly. We showed that. So we know that volume is directly proportional to temperature. And if we plot volume against temperature, you can see we can extrapolate the straight line. And what we will get to is minus 273.15, which is absolute zero or 0 Kelvin. So if we think about these a little bit more, so we know Boyle's law describes the behavior at constant temperature, and we have P times the pressure times volume is equal to a constant. We know that Charles' law is at constant pressure, so this gives us volume over temperature is equal to a constant. And if we combine these two equations, we get PV over T is equal to a constant. And this is an equation of states, and you will have met the concept of equation of states earlier in the lecture block when we talked about thermodynamics. And this leads us to the ideal gas law. And what we know is that the ideal gas law is given as PV equals nRT. And this is a very important law, and it's really important that you guys remember this. What we end up with is our P is our pressure, V is volume, the N is the number of moles, R is the gas constant, so this is our constant, which has a value of 8.314 joules per mole per Kelvin, and our T is our temperature. And this means that we can start to work out the differences in temperature, pressure, and volume between two gases. So we can actually write like this. So P1, V1 over T1 is equal to P2, V2 over T2, where the 2 tells us that's gas number 2, and the 1 tells us that's gas number 1. However, so this is great. We have a way to calculate things. This is really, really good news. Unfortunately, real gases do not follow the ideal gas law, particularly at high pressure. Some obey it better than others, but unfortunately, it turns out that it's not a good law. But it is, however, a good approximation. So it tells us information. It's nice and easy to use. So now we need to think about, well, what's the problem? Okay, so why do real gases not behave? So we have, for 1 mole of ideal gas, so all I've done here is rearrange the equation we had on the previous slide. We know that PV over RT equals 1. And if we plot PV over RT versus our pressure, we've got lots of different gases here. We know that an ideal gas would give a straight line because that's the ideal behavior. If you look, helium is not so bad, that does give us a straight line. But if you look at something like CH4, so methane, you can see that there is a really large deviation. You can see that we have quite good linear behavior at high pressures. But at low pressures, but the deviation, this effectively works out as low pressures, and at high temperatures, the deviation is much smaller. So what's wrong with the ideal gas law? Why doesn't this work? So from Charles's law, we know that the assumption is that at 0 K, the volume of a gas is 0. Okay, so at absolute 0, a gas has no volume. But we know this cannot physically be true. If I have a series of marbles and I compress them, I can only compress them so far. I'm never going to be able to compress those marbles to have no volume at all. The same is true for the gas. There are molecules in the gas. They're never going to have 0 volume. So this simply just cannot be true. There's always some volume there. And this means the law works at low pressures when the molecules are far apart. But at higher pressures, when we push the molecules close together, they start to interact with each other. And then this means that this law fails. So what we're saying is that the ideal gas law neglects intermolecular forces. And we're going to talk about intermolecular forces in the next lecture. So can we improve the ideal gas law? Well, of course we can. So you can see here, this is the pressure that's observed, and this is the ideal gas law. So we can see that typically the ideal gas law overestimates the real pressure, which is a good thing, because if I'm building a system that needs to withstand a certain pressure and I calculate it with the ideal gas law, I've got a buffer area. So this is why we still use the ideal gas equation. If it underestimated it, I could be in trouble because things might go bang. So what we need to do is we need to improve it by adjusting the pressure to account for intermolecular forces. And we also need to adjust the volume to account for the volume of a molecule. So we have some different versions here. There's the van der Waals equation, which is quite commonly used. And then there's Boyles Law equation, which is also used. And you can see here, these are more complex. Boyles Law takes into account temperature. We have minus NB term, which is the effective free space that a molecule can move in. And we also have this NB term, which is effectively the molecular volume. We also have this AN squared over V squared, and this is a effective reduction in pressure due to the intermolecular forces. And this is because as we get stuff closer together, the attractive forces are going to pull the molecules back into the container, and this reduces the pressure. So we have these two equations. If we now go back to our list here, we can see that this is our observed pressure. This is the pressure calculated with our ideal gas law. And what you can see here is that the van der Waals equation gives a better assumption, but actually it slightly underestimates. So it's still not a perfect match to this. And this is why we prefer to use the ideal gas law sometimes, because it gives us that little bit of buffer space. So next lecture, what we're going to start to look at is how we can use those, how we can start to make calculations with these, and how in the real world do we use these to get information. And we're also going to move on to starting to look at intermolecular forces, and that will start to lead us into looking at liquids in a bit more detail.